yako chini hapo. I welcome you to our today's class, and I'm glad that you are still following up, and also you are still with me in this class of Advanced Education Statistics, Unit Code EPM 9230. I'm your course lecturer, Dr. Wambeye Marakia, and we are still looking at the subtopic, the topic, sampling and variability. And today, I want us to move on and continue looking at this very topic. But today, we are looking at the subtopic, the non-probability and probability selection. It's a very important part of sampling and variability because it informs a researcher or a student of research why these probability sampling and probability sampling are very important in research. In a sample survey, data are collected for only a fraction, typically a very small fraction of units of the population. And in census, data are collected from all the units in the population. Now, the two types of sampling that we use in getting the fractions out of the population, we have non-probability sampling and probability sampling. Non-probability sampling provides a fast, easy, and inexpensive way of selecting units from the population, but uses a subjective method of selection. And in order to make inferences about the population from a non-probability sample, the data analyst must assume that the sample is representative of the population. Just a while. Probability sampling is more complex and it takes a longer time and is usually more costly. Because why is it more costly and it takes more longer time? Because units from the population are randomly selected and each unit's probability of selection can be calculated. Reliable estimates can be produced along with estimates of the sampling error, and inferences can be made about the population. And there are many different ways to selecting probability sample. The sample design chosen depends on such factors such as objective of the study. That's factor number one that you should consider when you are using probability sampling. And from the objective of the study, we get the research questions. What is the specific information that a researcher needs to be gathered? For example, if you need to compare subgroups from different region or age groups, a design that ensures sufficient sample size for each group is necessary. Second, on the level, on the objectivity, apart from the research question, you also need the level of precision required. How accurate do the estimates need to be? Studies requiring high precision and narrow confidence intervals will need a larger samples and potentially more complex design like stratification to reduce variance. Also, on the same we have objectivity, we need the analysis requirements. Will the analysis involve complex modeling or is primary for the generating simple population estimates? Some designs are better suited for advanced analytical techniques. 2, the nature of the population, the sampling frame you are dealing with. And this calls for, or you should look the availability of the sampling frame. Is there a complete, accurate, and accessible list of all the population elements? Second, geographical dispersion. Is the population clustered in a specific area? E.g., if you're doing research in education, students in schools, or if you are doing in hospitals, patients in hospitals, or are they widely scattered? This makes cluster sampling more efficient. Also, on the same, look at the homogeneity or the heterogeneity of the population. How similar or different are there in the population members on the key variables of interest? A highly heterogeneous population benefits greatly from stratification. Also, look at the presence of the natural subgroups. Does the population naturally fall into distinct, meaningful subgroups, which we call stratas, like income levels, business sectors, or age ranges? Number 3 factor we consider when you are doing probability sampling is the cost and resources. Look at the budget. What is the total financial resource available? More complex design like stratification or cluster sampling are often chosen to reduce costs. Number 2 on the cost and resources, we're looking at the time you are going to carry out the research. How quickly are the results needed? Cluster sampling can often be implemented faster than simple random sampling for a geographical dispersed population. Also, personal expert and expertise. Does the research team have the skills to design, implement, and analyze data from a complex sampling design? We move on to the factor number 4, operational and practical considerations. Look at the ease of access. Can interviewers easily reach the selected units for the face-to-face surveys? Number 2, burden on the respondent. Does the survey place a high burden, that's time sensitivity, on the respondents? This can affect response rates and may influence the approach. Also look at the expected response rate. Are certain subgroups less likely to respond? Oversampling these groups, a feature of stratified sampling, might be necessary to ensure they are adequately represented. Number 5, factor number 5 on probability sampling, why we should use probability sampling, is statistical efficiency. Now, we look at the desired precision, that is the sampling error, and this is the key trade-off. The goal is to minimize the sampling variance, that is error, for a given cost, or to minimize the cost to a desired level of precision. Stratified sampling is chosen when the primary goal is to increase the precision or to reduce the variance. by ensuring representation across all the key subgroups. Now, cluster sampling is chosen when the primary goal is to reduce the cost, even though it is typically increases the variance, that is less statistical efficiency compared to a simple random sample of the same size. Now, also we need to look at the need of the subgroup. We look at the domain with the subgroup we are carrying out the analysis on. If reliable estimates are needed for specific small subgroups of the population, stratification with this appropriate allocation are often essential. Number 6 factor, and I think this is the last one, administrative convenience. How easy is it to manage the entire process? Simple random is administratively straightforward if a good frame exists. Systematic sampling is very easy to implement once the first element is chosen. More complex design require more upfront planning and oversight. Now, what are the major types of probability sampling? The first one is simple random sampling. This is the most basic form of probability sampling. Every possible subset n individual from the population has an equal chance of probability of being chosen as the sample. It is equivalent to a lottery where every unit is assigned a number and a random number is generated to select the participant. It provides the foundation for all other methods, but it's often not the most efficient. When we use this method, we use it when the population is smaller and homogeneous and complete sampling frame is available. It's statistically straightforward, but can it be costly and impractical for large dispersed populations. The second type of probability sampling is systematic sampling. After selecting a random starting point from the sampling frame, every K unit is selected for the sample. The sampling interval K is calculated as the entire population over the sample size. Is subtraction where you take the entire population over a sample size. Now, the key feature of this of systematic sampling, it is simpler and more user-friendly than simple random sampling, especially in the field. However, it can introduce bias if the list has a hidden periodical pattern that coincides with the sampling interval. When do we use this one? When the population list is random or semi-random order. For example, we have the customer list, we have the phone books, or we have the production line. We have the third one, it's called stratified sampling. Now, the population is first divided into mutually exclusive and collectively exhaustive subgroups called stratas. And this is done basing on age, income, department, region, and extra. A separate probability sample, often called simple random sampling, is drawn from each strata. The key feature for stratified sampling, it ensures representation of the key subgroups and improves statistical precision. It means that it reduces sampling error by eliminating variability between the stratas. There are several types of stratified sampling. The first one is proportionate stratified sampling. The sample is from each strata is proportional to the strata size in the population. For example, if 20% of the population over 65, then 20% of the sample will be from that strata. Then we have this proportionate stratified sampling. The sample size from each strata is not proportional. This is done to ensure a large enough sample for a small but important subgroup to allow for reliable analysis within that subgroup. When we use this one, we use this one when the population has distinct important subgroups that you want to compare, or when you want to increase the overall precision of the estimates. Number 4, type of probability sampling. It's called cluster sampling, according to us here. The population is divided into natural occurring groups called clusters. And these clusters might include schools, cities, electoral districts, and extra. A random sample of cluster is selected, and all units within the chosen cluster are included in the sample. This is also known as single-stage cluster sampling. The key feature for this one, it is highly cost-effective and logistically convenient, especially when the population is large and geographically dispersed. However, it is less statistically efficient than the simple random sampling or stratified sampling. It leads to a higher sampling error because units within a cluster tend to be similar to each other. When can we use this process? It can be used when complete sampling frame for an individual element is unavailable or too expensive to create, or when the cost of data collection is of primary concern. The 5th type of probability sampling is multi-stage sampling. This is a complex extension of cluster sampling involving 2 or more stages of random sampling. It's progressively narrowed down the sample from a larger to a smaller unit. The major key feature of this one, it combines the cost of saving of cluster sampling with some of the precision of other methods by adding extra layers of randomization. When do we use this? For large national scale surveys where a single stage cluster sample will be too large and too costly. In this one, we have stage 1 cluster. We randomly select 10 cities from all the cities in a country. Then in stage 2, we use either systematic or simple random sampling within each of the 10 cities we selected in the first stage. Randomly select 5 neighborhoods. Then within each selected neighborhood, systematically sample 100 households to interview. On this multi-stage sampling, there is also what we call having finished this multi-stage sample, finished on the types of probability sampling. Also, we move on to get the types of non-probability sampling. On the non-probability sampling, we have 1, convenience sampling. The researcher selects individuals who are easiest to reach or mostly convenient available. The sample is drawn from the part of the population that is close at hand. When we use this type of non-probability sampling, we use it for preliminary testing of questionnaires or pilot studies, or when time and cost are extreme constraints. It is not suitable for making statistical inferences about the entire population. Also, another non-probability sampling is purposive. Sometimes we call it judgmental sampling. The researcher uses the expert judgment to select individuals who are most useful and appropriate for the study. The researcher deliberately chooses specific unique character or experience from the sample. When do we use this kind of sampling? When the researcher requires a specific type of a person who has specialized knowledge, that is expert in that field, or when they're studying a unique or hard to reach populations. Another type of non-probability sampling is snowballing sampling or chain referral sampling. The researcher starts with a few individuals who meet a criteria for a study and then asks them to refer other individuals who also meet the criteria. The sample snowball is assessed through referrals. When do we use this kind of non-probability sampling? It is ideal for studying hidden, hard to reach, or stigmatized population where no sample frame exists. We can have undocumented immigrants. We can have drug users, members of an exclusive club, or people with a rare disease. We use the snowball sampling to reach them. Also, there is another type of non-probability sampling called quota sampling. This is the non-sampling equivalent of stratified sampling. The population is first divided into natural, mutually exclusive subgroups, which have the like strata. Then the researcher conveniently selects a predetermined quota of the individuals from each subgroups. The major goal or the key feature for this is to create a sample that is proportional to the population in terms of key characteristics. That is the age, the gender, the race, and extra. But the final selection within the quota is non-random. When we use this quota sampling, when a stratified sample is desired, but full probability sample is too costly or too time-consuming, often we use this one in market research and opinion polls. Finally, we have self-selection sampling or volunteer sampling. The sample is made up of entire individuals who have volunteered to participate. The researcher publishes the needs for participants, and the people decide whether or not to put themselves forward. Common in a call-in radio TV stations where they are doing polls, online surveys open to public, or medical studies seeking volunteers are highly susceptible to bias. Now, I do a conclusion of this. I want to differentiate between the two. What is the difference between probability and non-probability sampling? We base on a feature. One of the feature is selection biases. In probability sampling, the units are randomly selected, but in non-probability sampling, researcher judgment or convenience applies. In both of these, also another feature that you can bring about their difference is the population that is chosen. In probability sampling, the population is known and it's non-zero. But in non-probability sampling, the population is unknown and often zero. Now, in another feature that can bring about the difference between probability sampling and non-probability sampling is the sampling frame. Whenever you are using probability sampling, the sampling frame is required. And when you are using non-probability sampling, no frame is required. Another feature that can bring the difference between the two is the biasness. In probability sampling, it minimizes selection because of selection biases. But in non-probability sampling, there is a very high risk of selection bias because of the methods that are used there. In another feature that can bring out the difference between probability sampling and non-probability sampling is the generalizability of the results. In probability sampling, the generalizability is high. Results can often be generalized to the entire population. But in non-probability sampling, generalizability is low. Results are typically not generalizable. Now, another feature that can bring out the difference between the two is primary use. In probability sampling, you use it in quantitative research, and we use it for making inferences. But in non-probability sampling, we use mainly for qualitative research, exploration, pilot studies, and we cannot make inference about the entire population. Then the last feature that can bring out the difference between the two is the cost and complexity. Generally, probability sampling has a higher cost and a higher complexity, and non-probability sampling have a lower cost, and the complexity is not so much. After finishing looking at the non-probability and probability sampling, allow me to move on to another area called sampling error. Because whenever you use the two types of sampling, there is an error you can introduce as a result of sampling. So allow me to discuss about the sampling error. What is a sampling error? It is the natural discrepancy or amount of error that exists between a sample statistics when you consider the sample mean and its corresponding population parameter. It arises solely because you are surveying a subset of the population rather than the entire population. When we survey the entire population, it's called a census, and it is not a mistake. When you generate this error, sometimes it's not a mistake. It is an inevitable consequence of sampling. There are major causes of non-sampling errors. Now, we are going to come back to sampling errors, but let me look at major causes of non-sampling errors. Now, these are errors in data acquisition, problems with respondents and instruments. When you've not done the sampling here, the errors here, coming in not as a result of the sample size, but as a result, one, the methods you use to acquire your data. We call them errors in that acquisition. These are problems with the respondents and instruments you are using. Now, errors can arise due to sampling frame. The list from which sample is drawn is incomplete or inaccurate. Second, selection bias. The methods of selecting respondents systematically excludes or underrepresents certain part of the population. Example, conducting an online survey about technology access, which automatically excludes students without reliable internet at home. This is a form of a digital divide bias. Then, non-response bias. Selection bias and non-response bias, which a researcher must be very careful to look at. A significant number of people selected for the sample do not respond. And these non-response are systematically different from those who do response. For example, in a survey about teachers' workload and burnout, teachers who are mostly overworked and stressed are less likely to have the time or energy to complete the survey. The results will reflect the views of the less stressed teachers underestimating the problem. Also, there are errors that come up because of the measurement errors, instruments, and respondent biasness. This is a huge category where the tool or the respondent provides inaccurate information. And they provide this inaccurate information due to the faulty questionnaire design. You have leading questions. Don't you agree that our fantastic new curriculum is improving students' outcome? This one is a leading question, and it might not get the answer. Or you have double-barreled questions. Do you find principal support? Do you find the principal supportive and accessible? A respondent might agree with one, but not the other. So double-barreled in question. Also, we have complex jargon in the questionnaire, asking parents about formative assessment benchmarks instead of class quizzes and progressive checks. Also, order of the questions on the questionnaire, asking about school funding cuts right before asking about teacher salary satisfaction can influence the respondent. So how you frame and put the questions on the questionnaire, it's very important, because when you don't frame the questions properly, it will introduce measurement errors, and this one will be a problem to when we are doing the analysis, because we might not get accurate information. Now, also we have the interviews biasness, interviewer bias. In this case, the interviewer's tone, demeanor, or expectation can influence the responses. An interviewer might unconsciously rephrase a question about discipline problems to sound more severe, leading the respondents to overstate the issues. Then we have the respondent bias. The first one is interviewer's bias, and this one the respondent bias. We might have social desirability bias. Respondents answer in a way they believe will make them look good. And also recall error, inability to accurately remember the past events. Also, we have the acquaintance bias. The acquaintance bias, the tendency for the respondent to agree with the statement regardless of their content. We had looked at the measurement errors. Now, I want us to move and look at errors in data processing and analysis. Errors in data processing and analysis. Data processing errors. These are mistakes made during data entry, coding, and cleaning phase. For example, a data clerk might miskey a student test as 85 instead of 58. Also, we have data analysis errors. The first one is data processing error. This one is data analysis errors using inappropriate statistical technique or model to analyze the data. They are different. Data processing errors and the data analysis errors, they are different. How do you minimize non-sampling errors? Carefully plan, pilot test questionnaires, train interviewers thoroughly, and carefully construct the sample frame. Number 2, good design. Use clear, natural, and simple language. Avoid leading questions. 3, minimize response rates. Use multiple contact method, that's email, phone, or mail, and offer incentives and send reminders. data quality checks. That's number 4. Data quality checks. Use double that entry, run logic checks, and clean the data meticulously before analysis. While sampling error tell you about the precision of your estimate, non-sampling errors threaten its fundamental accuracy. A highly precise estimate from a large sample can be completely wrong if it is riddled with non-sampling biases. Let me now move to the sampling error. Those were non-sampling errors. Sampling error is the natural discrepancy or amount of error that exists between a sample statistics and the true population parameter. Now, it is the difference between what you find studying a sample and what you have to find if you've studied the entire population. Now, the key idea here is this sampling error occurs solely because you are surveying a subset or a sample of a population, not a whole population. You should get that. It is not a mistake that you have a sampling error or a blunder of the researcher, but it's an inevitable and inherent part of sampling. It can be estimated and reduced, primarily by increasing the sample size, but it can never be eliminated entirely when working with a sample. Now, let's look at this sample error more critically. What is the cause of the sampling error? Or let me try to differentiate between the sampling error and non-sampling error. The cause of sampling error is not a variation from using a sample, and non-sampling errors occur because of human errors and procedural issues. In a census or the entire population, the sampling error is 0 because we don't have any sample we have used. But it is still present. It can still be present. The non-sampling error can still be present in a census because of the human errors. Now, the sampling error can be avoided, cannot be avoided. It's unavoidable. But it can be avoided in non-sampling error through careful work and all that. What are the most common measures of sampling error? The first common measure of a sampling error is called standard error, SE. This is the most fundamental measure of sampling error. It is the standard deviation of the sample distribution of a statistic. In simple terms, it measures how the sample statistics varies from one sample to another sample. This one quantifies the precision of your estimate. A smaller standard error indicates that your sample statistic is likely to be closer to the true population parameter. A larger standard error indicates a more variability and a less precision. Why is a standard error important? Because it quantifies the precision of your estimate. A smaller, as I said, standard error indicates that your sample statistic is likely closer to the true population. And the formula for a standard error is as we can see it here. SE Sometimes my pen takes time to come out. So this is the formula, the one I'm circling. It is the formula. And this formula is very important. Standard error equals to the sample standard deviation all over the root of the sample size. The root of the sample size. Now, let's see, we have some crucial insight from this formula. You should notice that N, which is the sample population, is a denominator. This is why a larger sample size leads to a smaller sample error. Also, when you double your sample size, does not cut the error by a half. It reduces by a factor of n of root n. It does not reduce it by a half. It reduces by a factor of root n. Now, I'm going to consider several examples here of using this formula and how to use them in our day-to-day life of research. A student higher education board, a state's higher education loans board, wants to know the average student loan debt for in a recent graduates. It's too expensive to survey all the 50,000 graduates. So they take a sample, a random sample. So they use a sample of 400. And from the sample of 200, from the sample of 400, the mean debt for the students is $28,500. And the standard deviation from this sample is $12,000. So we are going now to move on to start calculating the standard error for this population. So we take, our formula was N is standard deviation all over root of the sample size. So the standard deviation in this case is $12,000. Then divide by the root of the sample size, which is 400. When you take the root of 400, it will be 200, and this one remains. So when you divide these 12,000 by 12, you get 600. It should be 60. It should be 60. The standard error is $60. And this means that if the board were to take many random sample of 400 graduates, The average date from this sample will be varied by $60. From the true average of all the 50,000 graduates. Please, let me repeat here. The root of 400 is 20, not 200. The root of 400 is 20, not 200. And when you divide 12,000 by 20, you get 600. Please take note of that. Then the standard error is 600 because we were calculating the standard error. The standard error is 600. And this means that if the board were to take many random sample of 400 graduates, the average date from those samples will typically vary about by $600 from the true average date of 5,000 graduates. Then we move on to how we can use this information. This $600 is direct measure of the sampling error. The board can now report the estimate as, we estimate the average date to be $28,500 with a standard error of $600. Have another example. Example, estimating average teacher professional development. The TSC wants to understand the average number of hours teachers spend on professional development per year. Surveying all the 80,000 teachers in a state is too costly, so they commission a random samples survey. The population is 80,000 teachers. The sample size is 500 teachers they are surveying, and the mean sample is 42 hours, and the standard deviation is 15 hours. So this is the information we are going to use to calculate the standard error for surveying 500 teachers instead of taking the entire population. So our goal is to calculate the standard error to understand the precision of the estimate. So calculating the standard error will be, the error will tell us how much variation we expect in the sample mean. And here we have the entire formula, and then we put in, as I said before, the sample standard deviation is 15 and the sample mean is 500 teachers. So when you put all these in our formula, 15 over the root of 500, we get 15 over 22.35. Then we get 0.67 hours. So in reporting about this, but before we go to that, I want us to hold here this part because I'm introducing another part of the error called margin error. Margin error. Apart from the standard error, we also have the margin error, MOE. Now, this is the most practical and common reported measure, especially in the opinion polls, when we are reporting about the margin error. Now here, it provides about the plus or the minus range around the sample statistics. So in this one, we had calculated the standard error, but we are going to move on to calculate this margin of error, MOE. And whenever we are interpreting the margin of error, we use a confidence, and we use 95% of interpretation. So we are 95% confident that the true population value is within the sample results either positive, negative, the margin of error. Now, the formula for the margin of error is margin of error, MOE, equals to Z or Z times root P bracket 1 minus P all over sample size N. Now, the Z or the Z in these, that is always proportion of 95% confidence, as we saw in our other lesson where we were converting the Z for the raw data to Z scores. We saw that the proportion of the population that corresponds the 95 confidence level, it's 1.96. And in most cases, social science research uses the confidence, 95 confidence level. So when we are talking about the Z that corresponds the 95 confidence, it is 1.96 all the time. We will be using 1.96 when we are doing the conversion of the raw data to Z scores. We saw that the data that will lie between 95% confidence, it is 1.96. So when we are talking about 95% confidence, we always could be using 1.96 all the time. So in this case, our Z or our Z is going to be 1.96, and as we'll be seeing later, where I'll go to get the P is the proportion of the population. P is the proportion of the population that we are studying or that we are reporting on. Now, the proportion of the population, in this case, it might be 92%. When you convert this 92% to fraction, it's 0.72%. So you take the proportion of that population minus 1, minus the proportion divided by the N. Let me give an example here that is going to be, that can help us. In this example, we are getting the teacher support for a new technology initiative. In this, a large school district is considering a costly initiative to provide all classrooms with an interactive display boards. Before allocating the funds, the school board wants to gauge the teacher support. They randomly survey across the district. The population of the teachers in the districts is 2,500. Then they survey only 300 teachers, and the proportion of this population, P, their samples proportion, it is 72% of the teachers surveyed support the initiative. That means that 28% of the teachers did not support the initiative. So 72% of the surveyed teachers support the initiative. And we know the confidence level at 95%, the Z equals to 1.96. So what is our goal here? It is to calculate the margin of error, MOE, and also construct the confidence interval, CI, for the proportion. How do we proceed? The first thing is to calculate the MOE, calculate MOE here, the margin of error. The margin of error. And I said it's Z times root P, which is the proportion of the population. We are dealing with minus 1 minus P or over N. So in this case, we are going to have 1.96 corresponding to our Z value or our Z value. Then This 0.72, it is the 72%. The 72%. And where are we getting the 72%? It is here. The proportion of the population that supports the initiative. 72%. So we convert into fraction, which is going to be 0.2, 0.72. Then after working out at this level, we have taken 1 minus p, get 0.28 times 0.7 over 300. 300 is our sample population. Then work out this part, continue working out this part. When you take 0.72, 0.72 times 0.28, you get 0.2016 all over 300. Then you continue working out, then you get this part with your calculator, you get this part, then you work out the margin of error is going to be 0.0508. Then convert this one into percentage. Convert this one by multiplying this one by 100. You're able to get 5.1%. 5.1% rounded to the nearest number, 5.1%. Then how do we interpret? Before we interpret, let us do the construction of the confidence levels using what we have. So the confidence level is the P value or the percentage of the population that agrees minus or plus the margin of error. So in this case, we are going to get the lower bound and also we get the upper bound. The lower bound is going to be 72% minus 5.1%. Let me go back. 72% here is the proportion, the sample proportion that agrees with the initiative you are carrying out. And we have calculated, we see the margin of error. In this case, it is 5.1. 5.1%. So we are saying that we are now constructing the confidence interval where we are going to get the lower bound and the upper bound. Now the lower bound is going to be 72 minus 5.1, which is 66.9. And the upper bound is going to be 72 plus 5.1%, which is going to be 77.1%. Then we now move to the interpretation. How do we interpret this value? Now, based on your survey, we estimated that 72% of teachers support the new technology initiative. The margin of error of negative and positive 5.1 percentage points. This means that we are 95% confident that the true level of support among the teachers in the district, it is 66% on the lower and 77% on the upper. Is there any policy implication for this? Now, while a majority seems to support, the school boss must consider the wide range from 66. We have said this from 66.9 to 77.1. That is a very wide range. A policy expert must consider. The lower bound of the content level 66.9 suggests support could be as low as 2/3, while the upper bound 77.1% suggests that it could be as high as 3/4. This uncertainty might lead to them to conduct a further engagement or a larger survey before making a final decision that will affect this $1 project. Example number 3. Estimating the average school district expenditure per student. The state legislature is debating a new school funding formula. To understand the current baseline spending, they need to know the average expenditure per student across all the mid-sized school districts in the state. There are 200 such districts, and they decide to analyze a sample of their financial reports. From financial reports, the population is 200 mid-sized school districts in the state, and they decide to sample 40 districts. And the sample mean per student is $13,500. And the sample standard deviation per student is $2,800. The goal is to calculate the standard error and confidence intervals for the mean expenditure. This is how we proceed. First of all, we calculate the standard error. And the standard error here is the sample over the root of the sample, the standard deviation over the root of the sample. That is 2,800 is the standard deviation all over the root of 40. When you take 2,800 divided by 6.34, which is the root of 40, you get $442.7. Now, to calculate the margin of error, MOE, we take 95% confidence level. The Z-score at this level is 1.96. So we take the Z-score times the standard error. Here, 1.96 times the standard error, which is 4.27, you get $869.7. So from here, we move on to construct the margin, the confidence intervals. Because we have the margin of error, we have the standard error, we now move on to calculate our intervals. Now, these intervals will make us to make a decision as planners or as policymakers. The confidence intervals is the mean plus minus the margin of error. The mean margin of error. Now, the mean from what we had, the mean was 13,500 plus our margin of error. So the upper bound and the lower bound. So we start with the lower bound. The lower bound is 13,500 minus 867.7, which gives us 12,602. And then upper bound is 13,500 plus 867.7, which gives us $14,367. Now, how do we interpret these results? The financial analysis makes an average expenditure of 13,500 per student. However, due to variation between the districts, we are 95% confident that the mid-sized lie between 12,632 and 14,368. Now, if policy makers have to move on with this information, what would be the implication? This funding is critical for the funding formula debate, and legislature might argue that a new formula should aim to bring all this closer to this average, while others might focus on the range itself, suggesting aiding is needed for the district at a lower end. Now, the sampling error clearly shows that the exact average is uncertain, and the policy should be robust to this range, the range between $12,602 to $14,368. So it's very important that when the policy makers, policy formulators are formulating the policy, they should be able to look at that. Another example, we determine the proportion of students with reliable internet. In the wake of increased hybrid learning, a county education board is planning a program to subsidize home internet for low-income students. To budget effectively, they need to estimate the scale of the need. They conduct a random survey of students' families. All the population in that county, all the student population in that county, 50,000. They sample 1,200 families. And the sample proportion, that is 15% of the surveyed students report lacking of the internet access. Now, the confidence level at 95%, the Z equals to 1.96. We proceed to calculate our error, because the goal here is to calculate the margin error and a confidence interval, CI, for the proportion of the student without reliable internet. So here we have the margin of error equals to Z times proportion of the students, a proportion of the students, which is 50% that they lack internet. That was 50% times root times 1 minus 0.5. We have to go through the formula and then substitute everything here. 50% is the number of students that lack internet access at home. Then after substituting it clearly, you subtract, and then you come to this end. Then you put all this one in your calculator. Then you get that. Then here is the end of it. You convert it to percentage, then you get it is 2%. It is 2%, because this one you multiply by 100 to get to this is 2%. Multiply this one by 100, you get a 2%. Now, how do we use this 2%? Because imagine we now create the confidence intervals. This is create confidence intervals go to proportion of students without internet plus or minus margin of error, which is 15 minus 2 or 15 plus 2. That gives 13% or 17%. Now, our survey now indicates that 50% of the students lack reliable internet access with a margin of error of positive negative 2% points. We are 95% confident that the true proportion in the county is between 13% and 17%. For policy makers, the policy implication of this statement is the precise estimate is a right of budgeting. The board can now calculate the potential number of students affected. At the lower end is 13% of the 50, which is 6,500 students. And the upper bound is 17 of 50,000, which is 8,500. Instead of planning for a single number of 7,500 students based on 15% point, they can create a budget that is flexible enough to cover between 6,500 and 8,500 students. This directly accounts for the assembling error in their planning, ensuring the program is either gender funded or excessively overfunded. Now, I have a question for us to attempt. A university is evaluating a new funding model. A survey was conducted with a random sample of 608 students from a population of 150 students. Students responded to the statement, I support the new university funding model on a 5-point Likert scale. 1 equals to strongly disagree, and 5 strongly agree. And of course, we have others in between, 2 strong disagree, 3 neutral, and 1 strongly disagree, 2 disagree, 3 neutral, 4 agree, and 5 strongly agree. The sample data showed a mean of 3.56 and a standard deviation of 1.74. Now, required from you, calculate the standard error of the mean. Calculate the standard error of the mean. Part B, calculate the margin error for a 95 confidence interval, where Z-score equals to 1.96. Part C, construct the 95 confidence interval for the true population mean. Construct the 95% confidence interval for the true population mean. Interpret the confidence interval you calculated in part C above. Based on your results, write 2 policy recommendations for the university administration. Based on your results, write 2 policy recommendations for the university administration. This one brings us to the end of this subtopic today. Thank you very much for listening. Please attempt that question and let us meet in the next lecture, and God bless you.